This video here is for geometric sequences in series, which is 8.3. So geometric, it's a pattern that is essentially exponential. So arithmetic, remember, was linear, and geometric is exponential. All right, so it's a discrete pattern, and so there's a common ratio. That's a big thing that when we talk about, like in arithmetic, there's a common difference, which was D. The common ratio is R. All right, so when we reference common ratio, that's what we're talking about here. And this is what we're basically multiplying by. This is what we're multiplying by. Ratio. Okay, so an exponential pattern or a geometric pattern would be something of the nature like 4, and then we'd go 12. This is an example of it, 36. And so you're just multiplying by 3 here, so the common ratio would be 3. And so if I wanted to do the next term, I would have 108, and then 324, etc. And the pattern can continue. And so that it would have a common ratio of 3. So we can, of course, write this as an explicit or. We can have an explicit or we can have a recursive rule. And now, one thing that's different about geometric ratio is that is not the same as exponential is that the common ratio can actually be negative. You don't have to be positive. In an exponential function, you can't have a common ratio that's negative because it bounces back and forth because it goes up and down and up and down and up and down, like so. But with geometric, we can have a negative. So for instance, if I had, say, 5, negative 10, 20, negative 40, etc. And so the common ratio here would be negative 2. If you're wondering how to figure this common ratio out, R, you could just simply do any subsequent terms, but so like A2 divided by A1. So negative 10 divided by 5 is negative 2. And the common ratio can also be a fraction. It doesn't have to be a whole number. It could be a decimal. It could be a percentage. It can, obviously in application stuff, there's probably a good likelihood it's a percentage. Again, this is where you can do an amortization chart in an Excel document. When you have something like a mortgage payment or a car loan payment, and you want to know exactly how much value after you pay off what you pay off each month, because you have your interest, etc. So you can set yourself up at that. All right, so pretty neat actually application, and I know people who do this because it's not that hard actually to do once you actually understand what's going on. I have a couple of them for investments, and I have a couple for mortgage payments and that kind of stuff. I think I'm a math teacher, so I guess I'm sort of nerdy like that. All right. So I said that R could also be a fraction. So like, say if R is 1/2, let's make this 40 is the first term, and then that, if I'm multiplying by 1/2, and you can see, that it can keep on going. All right. Now, the recursive rule remains, again, of course, that we need to know the previous term. Okay, so the formula for a geometric one is that the next term is equal to that common ratio times the previous term. And of course, we must have a starting point. We have to have a starting point, otherwise it isn't going to work. So, for example, here, if I had a recursive rule written that it was 3, like so, and I know that I'm going to start at 4. So I could build my sequence here. It starts at 4. That's what A1 says. And so to get A2, according to this rule, is equal to 3 times 2 minus 1. So that's A1. So A1 is the 4, so it makes 12. And it can keep on with the pattern. So recursive rules are nice, especially when you have things that, of course, we said that you can't have an explicit rule, but this you do have it. Or if you were trying to blend two different ones together, such as an amortization chart. Now, if you go and want an explicit rule, well, actually, let's write a recursive rule from another example first. So let's go 10, 5, 2.5. So if I said write the recursive rule to this, then you would say, all right, well, I notice that this pattern, you're multiplying by a half. All right, so that makes it a geometric. So the recursive rule, I'm multiplying by 1/2 times the previous term, and I have to declare the first term to be 10. This is usually one of the higher scoring tests in this Data B class because obviously if you have these rules down and you can apply them, then you're golden. So that's recursive rule. All right. Now the explicit rule for a geometric, and it looks very much exponential. All right. So if I said to you, exponential functions a times b to the x, and a would be the beginning y value. So if you had something like this, and it goes, there's a and whatever we're multiplying by. A would be sort of like a subscript 0 in terms of this. But we don't use a subscript 0, at least in this textbook. We don't. It depends on your math teacher. It depends on your school. But in our textbook, it's going to use a subscript 1. So we're going to go ahead and stay with that. In my college days, when I was at Grand Valley, we used a subscript 0. So this is correct. This is what the textbook's going to use. But you could likewise write it like so. A subscript 0, and then it's r to the n. But this one is not what our textbook's going to use. I personally like that one, but that's not what our textbook's going to use. So I'm not going to try to confuse you on that. All right, so a subscript 1, r is the common ratio, and it's going to be to the power of n minus 1. By the way, this one over here looks just like that one, which is, of course, nice. All right, so let's go ahead and look at a pattern here. Let's say let's go with 10, 30, 90. You should know the next term is going to be 270 because we're multiplying by 3. All right, so a subscript n, the explicit rule here is going to be the beginning number. We're multiplying by 3, and the exponent's n minus 1, and that's it. That's all that you have for the explicit rule. That's it. That's how it goes. So, like, if I gave you a recursive rule and asked for the explicit rule, so if the recursive rule would say 4 a subscript n minus 1, and we start off at the term 7, then the explicit rule would be 7 times 4 to the n minus 1. Okay, and that's all it is. That's all it really is for the explicit rule. Arithmetic and geometric are pretty neat. They're nice ones that work out very well. And we need to be able to do the series too. The series, remember, is the summation of the terms. And so when you have a series, we are going to use sigma here, and it's 1 to n, whatever n is, and we're going to use k here. And so the formula, of course, is like so. There is a formula for this. So the geometric summation formula. Now this is for a finite, because we're going to deal with infinite in another video, but a finite means there's an n. So n is not infinity. So it has a definite end. So it doesn't go on forever. All right, so this is a situation where we have a sub 1, r to the n minus, and the formula then goes, well, the first term, 1 minus r to the nth power over 1 minus r. And it's a pretty neat formula. I'm not going to explain why it is. I mean, there's a pretty cool proof in the textbook at page 428 if you're interested in that. But so we're going to go ahead and add up these terms. We're going to show that it's true. We're going to do one, expand one out by hand, and then actually use the formula to do that also. All right. So again, it's the first term. So whatever that, well, if you start off at, say, k equals, say, 3, then you would be plugging in 3. But we're going to start off with 1. All right, and we'll do the first 5 terms of this pattern here. We've got k minus 1. Okay. Take the time to actually look at what this pattern is. All right, so first off, we recognize it is geometric. If I plug in 1 there, that is going to give me 4 times 2 to the 1 minus 1, which is equal to 4 times 2 to the 0. And 2 to the 0 is 1, so this is equal to 4. Realize you should pay attention to that, because that's where the your final exam potentially or test you would do some manipulation. So be careful of that. So the first term is 4, and it's doubling. So I want the first 5 terms from 1 to 5. So 8, 16, 32, 64. So this sigma here, remember that's a Greek letter, is telling me to add up from the first term, that's why the 1's there, all the way to the 5th term. That's what that's asking us to do. All right, that's what that notation represents. And all the way to the 5th term. If you're going into pre-calc or calculus, you'll see this sigma a lot. It's not that bad, but it's important that you understand what each of these things represent here. And so again, we go from the first term to the 5th term. And if we add this up, we're going to get, let's see, 40, 60, 124. Okay, I just had to just pause for a second and make sure that I did that right, and I did. So let's use our formula here. So our first term, again, we already declared that to be 4. We already figured that out. So it's 4, parenthesis, 1 minus r. r is 2 here. And it's to the nth power, so how many do we have? We have 5 terms. Okay, and it's all over 1 minus 2. So we need to take a second and we can plug this into a calculator. You could actually go ahead and know that 2 to the 5th power is 32. If you knew your multiplication facts, that 2 to the 4th power is 16. So 2 to the 5th power is 32. So 1 minus 32 is negative 31, all over 1 minus 2, which is negative 1. And multiply by the first term out there, and what a coinkydink, it is 124. So look at that, it still works. It's 124. So that rule for a finite geometric series works. So very nice. Now this rule, again, when we talk about a sub 1, 1 minus r to the nth, n is the number of terms. Okay, so this is going to be important because we can apply this rule when it doesn't necessarily start at the first term. So this is the number of terms, and this is a difficult thing for students to figure out, like initially. And then a sub 1 is just whatever the beginning one is. So we say a sub 1 in the formula here, but I'm going to give you an example where a sub 1 is not the beginning value here. So we've got sigma, and we're going to say k goes from 3 to 8. Okay, and now I'm going to give you a little bit of a different formula. So we're going to plug in, and we actually have to figure out what this first term is. All right, so let's say that this is 4 times 5. All right, and this is just going to be to k instead of k minus 1. So you got to be, because you could have k minus 1, you could have k plus 2, you could have k whatever up there. So we're going to, actually I'm going to make it a little different. I'm going to make it k plus 2 just for the fun of it. Okay, so that you actually have to plug it in. So the beginning term here is not 4. It is not 4. I cannot stress that enough. It is not 4. I'm going to plug in 3 to figure out what the first term is, again, because this is just simply the beginning term. So this is 4 times 5 to the 3 plus 2. Now I'm going to have to pause and use a calculator. So this is 4 times 5 to the 5th power, which is more than my mental capability. And that is 12,500. I think I could have actually done that. But, so 12,500. And then 1 minus r, so our common ratio here, what are we multiplying by? That is 5. And then we got to figure out how many terms there are. And the bottom is 1 minus 5 also. But this part up here, what is this part? What is n here? It is not 8. It is not 8. I stress that enough. So it goes from 8, the third term, to the 8th term. So a lot of students will be like, oh, that means that there are, 5. 8 minus 3 is 5. That seems logical. However, we're counting both ends. So we want the third term, the fourth term, the fifth term. My stylus is not that great. Sixth term, seventh term, and the eighth term. Okay, so 8 minus 3 is 5, but there are actually 6 terms. 1, 2, 3, 4, 5, 6, because you're counting both the third term and the 8th term. So we're actually adding, so you have 6 terms here. So n in this case is 6. So you would type this into a calculator and get your answer, because this is definitely a large number. Hold on. And so this is 4, 8, 8, 2, 5, 0, 0, 0. Okay, so it's 48,825,000. So that's a pretty big number, but that's what it is. Now, also, for those tech-savvy people and those who have a graphing calculator at home, it's important for us to understand these rules, because they can be, you can ask questions about them, and there's an understanding that goes along with it, and understanding what this truly means, because a lot of kids that just type into a calculator will not understand it. But you can, if you go to Math 0, for some of you, there is a summation that will show up on your graphing calculator, and you can go ahead and type that in, and it just, it won't use K, it'll say, you would type in X, okay, you go X equals 3, and you push the up arrow button, and you put 8 there, and then you put 4 times 5, and you'd use X again, and you would get the exact same answer. So your calculator can do that very nicely. But you need to know this part 2, the formula also. So if you're trying to figure out the kind of questions you can use to make sure that people know how to do this stuff, is actually they give you this stuff, and you got to figure out the equation or something like that. So you need to know both of those.